Hi class, this is your instructor, Skylar Huff, and welcome to Chapter 2, The Nature of Molecules and the Properties of Water. So here in this chapter, we're going to get into pretty much basic chemistry. So to understand how living systems are assembled, we must first understand a little about the atomic structure, about how atoms can be linked together by chemical bonds to make molecules, and about ways in which these small molecules are joined together to make larger molecules until we finally arrive at the structures of cells and then of organisms. So our study of life, therefore, begins with physics and chemistry. For many of you, this chapter will be a review of material encountered in other classes. Let us begin. So as we go through this chapter, there are 6 sections, and you will have questions from each of those 6 sections on your test. We'll start here with the nature of atoms. So any substance in the universe that has mass and occupies space is defined as matter. And all matter is composed of extremely small particles called atoms. Because of their size, atoms are difficult to study. In the early 20th century, scientists carried out the first experiments that revealed the physical nature of atoms. So to get along with what I'm saying, there is a figure called Figure 2.1, and this shows the Rutherford scattering experiment. So objects as small as atoms can be visualized only indirectly by using complex technology such as tunneling microscopy, which you can see here in Figure 2.2. We now know a great deal about the complexities of atomic structure, but the simple view put forth in 1913 by Danish physicist Niels Bohr provides a good starting point for understanding atomic theory. Bohr proposed that every atom possessed an orbiting cloud of tiny subatomic particles called electrons whizzing around a core like the planets of a miniature solar system. At the center of each atom is a small, very dense nucleus formed of 2 kinds of subatomic particles, protons and neutrons. And this is now showing you that exact image by way of Figure 2.3 with basic structure of atoms. Atomic number. Different atoms are defined by their atomic number, which is the number of protons. I repeat, the atomic number is the number of protons. I'll continue. Atoms with the same atomic number have the same number of protons, exhibit the same chemical properties, and are said to be the same element. An element is defined as any substance that cannot be broken down to any other substances by ordinary chemical means. Within the nucleus, the cluster of protons and neutrons is held together by a force that works only over short subatomic distances. Each proton carries a positive charge, and each neutron has no charge. Each electron carries a negative charge. Typically, an atom has 1 electron for each proton and is thus electrically neutral. The chemical behavior of an atom is due to the number and configuration of electrons, as we will see later in this very section. Next up is atomic mass. The terms mass and weight are often used interchangeably, but they have slightly different meanings. Mass refers to the amount of a substance, but weight refers to the force of the gravity exerts on a substance. So let me start that over. Mass and weight are often used interchangeably. However, mass refers to the amount of a substance, whereas weight refers to the force of gravity exerts on a substance. An object has the same mass whether it is on Earth or the Moon, but its weight will be greater on Earth because of Earth's gravitational force is greater than the Moon's. The atomic mass of an atom is equal to the sum of the masses of its protons and neutrons. atoms that occur naturally on Earth contain from 1 to 94 protons and up to 146 neutrons. And if you need help, you can look back, and it says the number of protons equals the number of electrons. Most, they're electrically neutral. The atomic number is equal to the number of protons, and every atom has a particular element has the same number of protons. So just keep in mind, an element is any substance that cannot be broken down into other substances by ordinary chemical means. So the mass of atoms and subatomic particles is measured in units called daltons. To give you an idea of just how small these units are, note that it takes 602 billion daltons to make 1 gram. A proton weighs approximately 1 dalton. Okay, it's actually 1.007 daltons, as does a neutron, 1.009 daltons. In contrast, electrons weigh only 1/1840th of a dalton, so they contribute almost nothing to the overall mass of an atom. The positive charges in the nucleus of an atom are neutralized or counterbalanced by the negatively charged electrons, which are located in regions called orbitals. So orbitals that lie at varying distances around the nucleus. So that's where those orbitals are found, in varying distances around the nucleus. Atoms with the same number of protons and electrons are electrically neutral. That is, they have no net charge and are therefore called neutral atoms. Electrons are maintained in their orbitals by their attraction to the positively charged nucleus. Sometimes other forces overcome this attraction, and an atom loses one or more electrons. In other cases, atoms gain additional electrons. Atoms in which the number of electrons does not equal the number of protons are known as ions, and they are charged particles. Again, ions are charged particles. An atom having more protons than electrons has a net positive charge and is called a cation. For example, an atom of sodium that has lost one electron becomes a sodium ion with a charge of +1 or 1+. An atom having fewer protons than electrons carries a negative charge and is called an anion. A chlorine atom, Cl, that has gained 1 electron becomes a chloride ion with a charge of -1 or 1-. On to isotopes. Although all atoms of an element have the same number of protons, they may not all have the same number of neutrons. Atoms of a single element that possesses different numbers of neutrons are called isotopes of that element. Most elements in nature exist as mixtures of different isotopes. Carbon, for example, has 3 isotopes, all containing 6 protons. And please see figure 2.4, which is now before you. Over 99% of the carbon found in nature exists as an isotope that also contains 6 neutrons. Because the total mass of this isotope is 12 daltons, 6 from protons plus 6 from neutrons, it is referred to as carbon-12 and is symbolized as 12C. Most of the rest of the naturally occurring carbon is carbon-13, an isotope with 7 neutrons. The rarest carbon isotope is carbon-14 with 8 neutrons. Unlike the other 2 isotopes, carbon-14 is unstable. This means that its nucleus tends to break up into elements with lower atomic numbers. This nuclear breakup, which emits a significant amount of energy, is called radioactive decay. And isotopes that decay in this fashion are radioactive isotopes. Some radioactive isotopes are more stable than others, and therefore they decay more readily. For any given isotope, however, the rate of decay is constant. The decay time is usually expressed as the half-life, the time it takes for 1/2 of the atoms in the sample to decay. Carbon-14, for example, often used in carbon dating of fossils and other materials, has a half-life of 5,730 years. A sample of carbon containing 1 gram of carbon-14 today will contain about 0.5 grams of carbon-14 after 5,730 years, and 0.25 grams in 11,460 years from now, and 0.125 grams 190 years from now, and so on. By determining the ratios of different isotopes of carbon and how other elements in biological samples and in rocks, scientists are able to accurately determine when these materials formed. Radioactivity has many useful applications in modern biology. Radioactive isotopes are one way to label or tag a specific molecule and then follow its progress either in a chemical reaction or in living cells and tissue. The downside, however, is that the energetic subatomic particles emitted by radioactive substances have the potential to severely damage living cells, producing genetic mutations, and at high doses, cell death. Consequently, exposure to radiation is carefully controlled and regulated. Scientists who work with radioactivity follow strict handling protocols and wear radiation-sensitive badges to monitor their exposure over time to help ensure a safe level of exposure. The key to chemical behavior of an atom lies in the number and arrangement of its electrons in their orbitals. The Bohr model of the atom shows individual electrons as following distinct circular orbits around a central nucleus. The trouble with this simple picture is it doesn't reflect reality. Modern physics indicates that we cannot pinpoint the position of any individual electron at any given time. In fact, an electron could be anywhere, from close to the nucleus to infinitely far away from it. A particular electron, however, is more likely to be in some areas than others. An orbital is defined as the area around a nucleus where an electron is most likely to be found. These orbitals represent distributions for electrons, that is, regions more likely to contain an electron. Some electron orbitals near the nucleus are spherical, or s orbitals, whereas others are dumbbell-shaped, known as p orbitals. Please see figure 2.5, shown to you now. And still other orbitals farther away from the nucleus may have different shapes. Regardless of its shape, no orbital can contain more than 2 electrons. Almost all of the volume of an atom is empty space. This is because the electrons are usually far away from the nucleus, relative to its size. If the electron of an atom were the size of a golf ball, the orbit of the nearest electron would be a mile away. Consequently, the nuclei of 2 atoms never come close enough in nature to interact with each other. It is for this reason that an atom's electrons, not its protons or neutrons, determine its chemical behavior, and it also explains why isotopes of an element, all of which have the same arrangement of electrons, behave the same way chemically. Because electrons are attracted to the positively charged nucleus, it takes work to keep them in their orbitals, just as it takes work to hold up a grapefruit in your hand against the pull of gravity. The formal definition of energy is the ability to do work. The grapefruit held above ground is said to possess potential energy because of its position. If you release it, the grapefruit falls and its potential energy is reduced. On the other hand, if you carry the grapefruit to the top of a building, you would increase its potential energy. Electrons also have potential energy that is related to their position. To oppose the attraction of the nucleus and move the electron to a more distant orbital requires an input of energy, which results in an electron with greater potential energy. The chlorophyll that makes plants green captures energy from sunlight during photosynthesis in this way. As you'll see in Chapter 8, light energy excites electrons in the chlorophyll molecule. Moving an electron closer to the nucleus has the opposite effect. Energy is released, usually as radiant energy, such as heat or light, and the electron ends up with less potential energy. And you can see this shown to you in figure 2.6 as shown now. One of the initially surprising aspects of atomic structure is that electrons within the atom have discrete energy levels. These discrete levels correspond with quanta, singular, quantum, which means a specific amount of energy. To use the grapefruit analogy again, it is as though a grapefruit could be raised to particular floors of a building. Every atom exhibits a ladder of potential energy values, a discrete set of orbitals at particular energetic distances from the nucleus. Because the amount of energy an electron possesses is related to its distance from the nucleus, electrons that are the same distance from the nucleus have the same energy, even if they occupy different orbitals. Such electrons are said to occupy the same energy level, and the energy levels are denoted with letters K, L, M, and so on. And you can see that here in figure 2.6. Be careful not to confuse energy levels, which are drawn as rings to indicate an electron's energy, with orbitals, which have a variety of three-dimensional shapes and indicate an electron's most likely location. Electron orbitals are arranged so that as they are filled, this fills each energy level in successive order. This filling of orbitals and energy levels is what is responsible for the chemical reactivity of elements, which is what we're getting to now. During some chemical reactions, electrons are transferred from one atom to another. In such reactions, the loss of an electron is called oxidation, and the gain of an electron is called reduction. During some chemical reactions, electrons are transferred from one atom to another. In such reactions, the loss of an electron is called oxidation, and the gain of an electron is called reduction. Notice that when an electron is transferred in this way, it keeps its energy of position. In organisms, chemical energy is stored in high-energy electrons that are transferred from one atom to another in reactions involving oxidation and reduction. And this will be described more so in Chapter 7. When the process of oxidation and reduction are coupled, which often happens, one atom or molecule is oxidized while the other is reduced in the same reaction. We call these combinations redox reactions. 94 elements occur naturally, each with a different number of protons and a different arrangement of electrons. When the 19th century Russian chemist Dmitry Mendeleev arranged the known elements in a table according to their atomic number, he discovered one of the greatest generalizations of science. The elements exhibit a pattern of chemical properties that repeats itself in groups of 8. This periodically repeating pattern lent the table its name, the periodic table of elements, as shown in figure 2.7, which you now see. The 8-element periodicity that Mendeleev found is based on the interactions of the electrons in the outermost energy level of the different elements. We call these valence electrons, and their interactions are the basis for the differing chemical properties of elements. For most atoms important to life, this valence shell contains no more than 8 electrons. The chemical behavior of an element reflects how many of the 8 positions are filled. Elements with 8 electrons in their outer energy level, 2 for helium, they are inert or non-reactive. These elements, such as helium, neon, argon, and so on, are called noble gases. In contrast, elements with only 7 electrons in their outer energy level, such as fluorine, chlorine, bromine, are highly reactive. They tend to gain the extra electron needed to fill the energy level. Elements with only 1 electron in their outer shell, such as lithium, sodium, and potassium are also very reactive, but those tend to lose the single electron in their outer level. These observations led to the so-called octet rule or rule of 8. Atoms tend to establish completely full outer energy levels. For main group elements of the periodic table, the rule of 8 requires 1 filled s orbital and 3 filled p orbitals. However, if you look at figure 2.8, you will see this. The exception is helium, which needs only 2 electrons to fill the 1s orbital. Most chemical behavior of biological interests can be predicted by this simple rule, combined with the tendency of atoms to balance out positive and negative charges. For instance, in section 2.3, we will see that sodium ions and chloride ions can react to form table salt, which is sodium chloride. Of the 94 naturally occurring elements, only 12 are found in living systems in more than trace amounts or higher. These elements all have atomic numbers less than 21 and thus low atomic masses. The distribution of elements in living systems is obviously not random. The most common elements in cells are not the elements that are the most abundant in Earth's crust. Of these 12 common elements, the first 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up 96.3% of the weight of your body. And thereafter you have oxygen, carbon, nitrogen, hydrogen, phosphorus, sulfur, potassium, sodium, calcium, magnesium, iron, and chlorine. So the majority of molecules in your body are composed of carbon, which we call organic compounds. These organic compounds contain primarily these 4 elements: oxygen, carbon, hydrogen, nitrogen. Since water is the most common molecule in your body, oxygen, not carbon, is the most abundant element in your body. Some trace elements such as zinc and iodine play critical roles in living processes, even though they are present in tiny amounts. Iodine deficiency, for example, can lead to enlargement of the thyroid gland, causing a bulge at the neck called a goiter. Now let's get on into what are called chemical bonds. A group of atoms held together by energy in a stable association is called a molecule. When a molecule contains atoms of more than one element, it is called a compound. So one more time, a group of atoms held together by energy in a stable association is called a molecule. And when a molecule contains atoms of more than one element, it is called a compound. The atoms in a molecule are joined by chemical bonds. These bonds can result when atoms with opposite charges attract each other, i.e., ionic bonds. When 2 atoms share one or more pairs of electrons, covalent bonds, or when atoms interact in other ways. We will start by examining ionic bonds, which form when atoms with opposite electrical charges or ions attract. Common table salt, the molecule sodium chloride, NaCl, is the lattice of ions in which atoms are held together by ionic bonds. Please see figure 2.9 shown to you here. Sodium has 11 electrons, 2 in the inner energy level, 8 in the next level, and 1 in the outer valence level. The single unpaired valence electron has a strong tendency to join with another unpaired electron in another atom. A stable configuration can be achieved if the valence electron is lost to another atom that also has an unpaired electron. This loss of this electron results in the formation of a positively charged sodium ion. The chlorine atom has 17 electrons. I again say, the chlorine atom has 17 electrons. 2 in the K level, 8 in the L level, 7 in the M level, And as you can see here in figure 2.9, one of the orbitals in the outer level has an unpaired electron. It's that red circle you see. The addition of another electron fills that level and causes a negatively charged chloride ion to form. When placed together, metallic sodium and gaseous chlorine react swiftly and explosively as the sodium atoms are oxidized, donating electrons to the chlorine atoms, reducing them, and forming sodium and chloride ions. Because the opposite charges attract, the sodium and chloride remain associated in an ionic compound, sodium chloride, which is electrically neutral. The electrical attractive force holding sodium chloride together, however, is not directed specifically between individual sodium and chloride ions, and no individual sodium chloride molecules form. Instead, the force exists between any one ion and all neighboring ions of the opposite charge. The ions aggregate in a crystal matrix with precise geometry. Such aggregations are what we know as salt crystals. If a salt such as sodium chloride is placed in water, however, the electrical attraction of water molecules disrupts the forces holding the ions in the crystal matrix, causing the salt to dissolve in a roughly equal mixture of free sodium and chloride ions. Because living systems always include water, ions are more important than ionic crystals. Important ions in biological systems include calcium ions, which are involved in cell signaling, potassium ions, and sodium ions, which are involved in the conduction of nerve impulses, which you all will learn about later on. Not in this lecture, however. So next is the covalent bond. Covalent bonds are formed when two atoms share one or more pairs of valence electrons. Consider gaseous hydrogen, H2, as an example. Each hydrogen atom has an unpaired electron and an unfilled outer energy level. For these reasons, the hydrogen atom is unstable. However, when two hydrogen atoms are in close association, each atom's electron is attracted to both nuclei. In effect, the nuclei are able to share their electrons. The result is a diatomic or a two-atom molecule of hydrogen gas. The molecule formed by the two hydrogen atoms is stable for three reasons. It has no net charge, the octet root is satisfied, and it has no unpaired electrons. Unlike ionic bonds, covalent bonds are formed between two individual atoms, giving rise to true discrete molecules. The strength of a covalent bond depends on the number of shared electrons. Thus, double bonds, which satisfy the octet rule by allowing two atoms to share two pairs of electrons, are stronger than single bonds, in which only one electron pair is shared. In practical terms, more energy is required to break a double bond than to break a single bond. And the strongest covalent bonds are triple bonds, such as those that link two nitrogen atoms of nitrogen gas molecules, N2. Covalent bonds are represented in chemical formulas as lines connecting atomic symbols. Each line between two bonded atoms represents the sharing of one pair of electrons. The structural formulas of hydrogen gas and oxygen gas are, well, as you see, H, H, or O, O, respectively. And their molecular formulas are just a bit different. And are those shown here? They are shown right there. So you have H sub 2, O sub 2, and N sub 2. So there you have it. Single, double, and triple covalent bonds. A vast number of biological compounds are composed of more than two atoms. An atom that requires 2, 3, or 4 additional electrons to fill its outer level completely may acquire them by sharing its electrons with 2 or more atoms. For example, the carbon atom contains 6 electrons, 4 of which are in its outer energy level, and 2 are unpaired. To satisfy the octet rule, a carbon atom must form 4 covalent bonds. Because 4 covalent bonds may form in many ways, carbon atoms are found in many different kinds of molecules, such as Ch2, which is carbon dioxide, Ch4, which is methane, and C2H5OH, which is ethanol. That's alcohol. And those are just a few examples. Polar and non-polar covalent bonds. Atoms differ in their affinity for electrons, a property called electronegativity. And in general, electronegativity increases left to right across the row of the periodic table and decreases down the column. Thus, the elements in the upper right corner have the highest electronegativity. For bonds between identical atoms, for example, such as 2 hydrogen or 2 oxygen atoms, the affinity for electrons is obviously the same and the electrons are equally shared. Such bonds are termed non-polar. Non-polar covalent bonds equal sharing of electrons, resulting in compounds H2 or O2, but also referred to as non-polar. For atoms that differ greatly in electronegativity, electrons are not shared equally. The shared electrons are more likely to be closer to the atom with the greater electronegativity and less likely to be near the atom of lower electronegativity. In this case, although the molecule is still electrically neutral, i.e. the same number of protons and neutrons, the distribution of charge, however, is not uniform. So this unequal distribution results in regions of partial negative charge near the more electronegative atom, and the regions of partial positive charge near the less electronegative atom. Such bonds are termed polar covalent bonds, and the molecules polar molecules, such as polar covalent bonds, unequal sharing of electrons. So when drawing these partial charges are usually symbolized using the lowercase Greek letter delta. The partial charge seen in a polar covalent bond is relatively small and far less than the unit charge of an ion. For biological molecules, we can predict the polarity of bonds by knowing the relative electronegativity of a small number of important atoms. And you can see this in table 2.2. Not shown here. So notice, however, carbon and hydrogen differ slightly in electronegativity, and this small difference is negligible, and carbon-hydrogen bonds are considered nonpolar. Because of its importance in chemistry of water, we will explore the nature of polar and nonpolar molecules in section 2.4. Water, which is H2O, is a polar molecule with electrons more concentrated around the oxygen atom. The formation and breaking of chemical bonds, which is the essence of chemistry, is termed chemical reaction. All chemical reactions involve the shifting of atoms from one molecule or ionic compound to another without changing the number or identity of the atoms. For convenience, we refer to the original molecules before the reaction starts as reactants. I say again, for convenience, we refer to the original molecules before the reaction starts as reactants, located in this example on the left. The molecules resulting from the chemical reactions as products, and that's shown here in the example on the right. So for example, you have 6 water molecules plus 6 carbon dioxide molecules, those 2 reactants yielding 2 products. We have glucose and oxygen, C6H12O6 plus 6O2. You may recognize this equation as a simplified form of the photosynthesis reaction in which water and carbon dioxide are combined to produce glucose and oxygen. Most animal life ultimately depends on this reaction, which takes place in plants. You'll learn about this in Chapter 8. To the extent to which chemical reactions occur is influenced by 3 important factors. I repeat, the extent to which these chemical reactions occur is influenced by three important factors, one being temperature. Typically, heating the reactants increases the rate of reaction because the reactants collide with one another more often. Concentration of reactants and products. So reactions proceed more quickly when more reactants are available, allowing more frequent collisions. And catalysts. A catalyst is a substance that increases the rate of a reaction, sometimes referred to as being an enzyme, you all. And it doesn't alter the reaction's equilibrium between reactants and products, but it does shorten the time needed to reach equilibrium, i.e. they speed up that rate of reaction while lowering that activation energy, the energy needed to start the reaction. So in most living systems, proteins called enzymes catalyze almost every chemical reaction. So many reactions in nature are reversible. This means that the products themselves may be reactants, allowing the reaction to proceed in reverse. So given that, you have the extent of chemical reactions here, and those three factors that may influence them. Now let's get to reversing reactions. They don't show the reverse to reaction. So you have reactants C6H12O6 plus 6O2 yielding 6H2O plus 6CO2. And that is the reaction shown a moment ago in reverse, which I don't have to show you it here in reverse, but you would merely start with glucose and oxygen and yield the water and 6CO2. So the reaction is a simplified version of the oxidation of glucose by cellular respiration, in which glucose is broken down into water and carbon dioxide in the presence of oxygen. And virtually all organisms carry out forms of glucose oxidation, and you'll find this out in Chapter 7. Water. Of all the common molecules, only water exists as a liquid at the relatively low temperatures that prevail on Earth's surface. 3/4 of Earth is covered by liquid water. You can see figure 2.10. There at A, you have solid, snow and ice. At B, liquid. And then you have at C, the liquid becomes steam and water rises above 100 degrees Celsius. Liquid when the temperature is above 0 degrees Celsius, and water becomes crystals known as snow and ice below 0 degrees Celsius. When life was beginning, water was provided a medium in which other molecules could move around and interact without being held in place by strong covalent or ionic bonds. Life evolved in water for 2 billion years before spreading to land. And even today, life is inextricably tied to water. About 2/3 of any organism's body is composed of water, and all organisms require a water-rich environment either inside or outside them for growth and reproduction. It is no accident that tropical rainforests are bursting with life, whereas dry deserts appear almost lifeless except when water becomes temporarily plentiful after a rainstorm. Water has a simple molecular structure consisting of an oxygen atom bound to 2 hydrogen atoms by 2 single covalent bonds. And you'll see this in figure 2.11 now shown. The resulting molecule is stable, has no unpaired electrons, and carries no net electrical charge. The electronegativity of oxygen is greater than that of hydrogen, so the bonds between these atoms are highly polar. The polarity of water molecules underlies water's chemistry and the chemistry of life. Consider the shape of a water molecule. It has 2 covalent bonds that have a partial charge at each end, shown there. So slightly more negative at the oxygen and slightly more positive at the hydrogen end. The most stable arrangement of these charges is a tetrahedron, which is a pyramid with a triangle at its base, in which 2 negative and 2 positive charges are approximately equidistant from one another, with the oxygen atom at the center of the tetrahedron. This arrangement of partial charges allows water molecules to interact, forming weak chemical associations called hydrogen bonds, our third type of bond. The particularly negative oxygen atom in one molecule is attracted to the partial positive hydrogen atoms of another water molecule. So in all phases, every water molecule is interacting with multiple other water molecules, and as we shall see, hydrogen bonding leads to some interesting properties. Hydrogen bonding is not limited to water molecules. Any molecule with hydrogen attached to a more electronegative atom, usually oxygen or nitrogen, can potentially form hydrogen bonds. While these are too weak to form stable molecules by themselves, like Velcro, they can form and close associations by the sum of many weak interactions. A hydrogen bond has only 5 to 10% of the strength of a covalent bond, but hydrogen bonds are critical for DNA and protein structure, and thus they underlie much of the organization of living systems. Now let's get to properties of water. The hydrogen bonding of water means that water molecules are attracted to one another. That is, water is cohesive. Each hydrogen bond is individually very weak and transient, lasting on average only 100 billionth of a second. The cumulative effects of large numbers of these bonds, however, can be enormous. Water forms an abundance of hydrogen bonds, which are responsible for many of its important physical properties, and those are shown in Table 2.3, which I don't have for you, unfortunately, but you can find it in your text. Water's cohesion is responsible for it being a liquid, not a gas, at moderate temperatures. The cohesion of water is also responsible for its surface tension. So let's get to surface tension here. There we go. Small insects can walk on water, such as you see here in figure 2.13. Because the air-water interface, all the surface water molecules are hydrogen bonded to molecules below them. Water molecules are also adhesive, so it's the polarity of water that causes it to be attracted to another polar molecule, to other polar molecules as well. This attraction for other polar substances is called adhesion. Water adheres to any substance with which it can form hydrogen bonds. This property explains why substances containing polar molecules can get wet when they are immersed in water, but those that are composed of non-polar molecules, such as oils, do not. The attraction of water to substances that have electrical charges on their surface is responsible for capillary action. If a glass tube with a narrow diameter is lowered into a beaker of water, the water will rise in the tube above the level of water in the beaker because of the adhesion of water to the surface, to the glass surface, drawing water upward. And it's stronger than the force of gravity, pulling it downward. So the narrower the tube, the greater the electrostatic forces between the water and the glass, and the higher the water rises. And this is shown here for you on the right hand side on figure 2.14. So we will see how plants use this principle for water transport. If you take biology 2, you will see that there. That will not be taught in this course. Capillary action causes the water within the narrow tube to rise above the surrounding water level. So that's adhesion. So water moderates temperature through two properties: its high specific heat and its high heat of vaporization. Water also has the unusual property of being less dense in its solid form, ice, than it is as a liquid. So water acts as a solvent for polar molecules and exerts an organizing effect on nonpolar molecules. All these properties result from its polar nature. The temperature of any substance is measured by how rapidly individual molecules are moving. In the case of water, a large input of thermal energy was required to break many hydrogen bonds that keep individual water molecules from moving about. Therefore, water is said to have a high specific heat, which is defined as the amount of heat 1 gram of a substance must absorb or lose to change its temperature by 1 degree Celsius. Specific heat measures the extent to which a substance resists changing its temperature when it absorbs or loses heat. Because polar substances tend to form hydrogen bonds, the more polar it is, the higher specific heat. Specific heat of water is twice that of most carbon compounds and 9 times that of iron. Only ammonia, which is more polar than water and forms very strong hydrogen bonds, has a higher specific heat than water. Still, only 20% of hydrogen bonds are broken as the water heats up from 0 degrees to 100 degrees Celsius. Because of its high specific heat, water heats up more slowly than almost any other compound and holds its temperature longer. Because organisms have a high water content, water's high specific heat allows them to maintain a relatively constant internal temperature. The heat generated by the chemical reactions inside the cells would destroy the cells if not for the absorption of this heat by the water within them. The heat of vaporization is defined as the amount of energy required to change 1 gram of a substance from a liquid to a gas. A considerable amount of energy, 586 calories, is required to accomplish this change in water. As water changes from a liquid to a gas, it requires energy in the form of heat to break its many hydrogen bonds. The evaporation of water from a surface cools that surface. So the evaporation of water from a surface cools that surface. And many organisms dispose of excess body heat by evaporative cooling. For example, through sweating in humans and many other vertebrates. At low temperatures, water molecules are locked into a crystal-like lattice of hydrogen bonds, forming solid ice. Interestingly, ice is less dense than liquid water because the hydrogen bonds in ice space the water molecules relatively far apart. This unusual feature enables icebergs to float. If water did not have this property, nearly all bodies of water would be ice, with only the shallow surface melting every year. The buoyancy of ice is important ecologically because it means bodies of water freeze from the top down, not the bottom up, because ice floats on the surface of lakes in the winter and the water beneath remains liquid. Fish and other animals keep from freezing. Water molecules gather closely around any substance that bears an electric charge, whether that substance carries a full charge or a charge separation. For example, sucrose, which is table sugar, is composed of molecules that contain polar hydroxyl groups. A sugar crystal dissolves rapidly in water because water molecules can form hydrogen bonds with individual hydroxyl groups of the sucrose molecules. Therefore, sucrose is said to be soluble in water. Water is termed solvent and sugar is termed solute. Every time a sucrose molecule dissociates or breaks away from a solid sugar crystal, water molecules surround it in a cloud, forming a hydration shell that prevents it from associating with other sucrose molecules. Hydration shells also form around ions such as sodium and chloride. And you can see this shown to you in figure 215 as shown here. And I can show it again here. Water molecules always tend to form the maximum possible number of hydrogen bonds. When non-polar molecules such as oils, which do not form hydrogen bonds, are placed in water, the water molecules act to exclude them. The non-polar molecules aggregate or clump together, thus minimizing their disruption of the hydrogen bonding in water. In effect, they shrink from contact with water, and for this reason they are referred to as being hydrophobic. In contrast, Polar molecules, which readily form hydrogen bonds in water, are said to be hydrophilic. The tendency of nonpolar molecules to aggregate in water is known as hydrophobic exclusion. By forcing the hydrophobic portions of molecules together, water can influence the shape of these molecules, and this property is important to the structure of proteins, DNA, and biological membranes. In fact, the interaction of nonpolar molecules in water is critical to living systems. Lastly, water can form ions. The covalent bond holding one hydrogen atom to the oxygen atom in water molecule can spontaneously be broken. In pure water, at 25 degrees Celsius, only 1 out of every 550 million water molecules undergoes this process. When it happens, a proton, which is a hydrogen atom nucleus, dissociates from the molecule. Because the dissociated proton lacks the negatively charged electron it was sharing, its positive charge is no longer counterbalanced, and it becomes a hydrogen ion. The rest of the dissociated water molecule, which has retained the shared electron from the covalent bond, is negatively charged and forms a hydroxide ion. This process of spontaneous ion formation is called ionization, which you can see in your text. At 25 degrees Celsius, 1 liter of water contains 1/10,000,000th, or 10 to the negative 7th of mole of hydrogen ions. A mole is defined as the weight of a substance in grams that corresponds to the atomic mass of all of the atoms in the molecule of that substance. In the case of the hydrogen ion, the atomic mass is 1, and a mole of hydrogen ions would weigh 1 gram. 1 mole of any substance always contains 6.02 times 10 to the 23rd molecules of that substance. Therefore, a molar concentration of hydrogen ions in pure water is represented as the hydrogen ion, in brackets here, and it is 10 to the negative 7 moles per liter. So in reality, the hydrogen ion usually associates with another water molecule to form a hydronium ion, which is H3O positive. So the concentration of hydrogen ions and concurrently hydroxide ions in a solution is described by the terms acidity and basicity, respectively. Pure water having hydrogen ions of 10 to the negative 7 moles per liter is considered to be neutral, that is, neither acidic or basic. Recall that for every hydrogen ion formed when water dissociates, a hydroxide ion is also formed, meaning that the dissociation of water produces hydrogen ions and hydroxide ions in equal amounts. The pH scale, which is shown in figure 2.16, now shown to you here, is a more convenient way to express the hydrogen ion concentration of a solution. The scale defines pH, which stands for power of hydrogen, as the negative logarithm of the hydrogen ion concentration in a solution. And I'll go back just a bit. So this is what it's referred to as the negative log of the hydrogen ion concentration in the solution. Because of the logarithm of the hydrogen ion concentration is simply the exponent of the molar concentration of the hydrogen ions, the pH equals the exponent times -1. For water, therefore, a hydrogen ion concentration of 10 to the negative 7 moles per liter corresponds with a pH value of 7. This is the neutral point, a balance between hydrogen ions and hydroxide ions on the pH scale. This balance occurs because the dissociation of water produces equal amounts of hydrogen ions and hydroxide ions. Note that because the pH scale is a logarithmic scale, a difference of 1 on the scale represents a 10-fold change in hydrogen ions, you all. A solution with a pH of 4, therefore, has 10 times the hydrogen ions of a pH with a pH of 5 and 100 times the hydrogen ion concentration of a solution with a pH of 6. Now on to what are referred to as acids. Any substance that dissociates in water to increase the hydrogen ion concentration and lower the pH is called an acid. The stronger an acid is, the more hydrogen ions it produces, and the lower its pH. For example, the hydrochloric acid, which is abundant in your stomach, ionizes completely in water. A dilution of 10 to the minus 1 moles per liter of hydrochloric acid dissociates to form 10 to the negative 1 mole per liter of hydrogen ions, giving the solution a pH of 1. The pH of champagne, which bubbles because of the carbonic acid dissolved in it, is about 2. Bases. A substance that combines with hydrogen ion when dissolved in water and thus lower the hydrogen ion concentration is called a base. Therefore, basic or alkaline solutions have pH values above 7. Very strong bases such as sodium hydroxide, NaOH, have pH values of 12 or more. Many common cleaning substances such as ammonia and bleach accomplish their action because of their high pH, which you all can see at the bottom right there. And now on to buffers. The pH inside most living cells and in the fluid surrounding cells in multicellular organisms is fairly close to neutral, which is 7. Most of the enzymes in living systems are extremely sensitive to pH. Often, even a small change in pH will alter their shape, thereby disrupting their activities. For this reason, it is important that a cell maintaining a constant pH level. And again I say, for this reason, it is important that a cell maintain a constant pH level. But the chemical reactions of life constantly produce acids and bases within cells. Furthermore, many animals eat substances that are acidic or basic. Cola drinks, for example, are moderately strong, although dilute acidic solutions. I don't recommend these. Despite such variations in the concentrations of hydrogen ions and hydroxide ions, the pH of an organism is kept at a relatively constant level by buffers. Please see figure 2.17. So a buffer is a substance that resists changes in pH. Buffers act by releasing hydrogen ions when a base is added and absorbing hydrogen ions when an acid is added, and the overall effect of keeping hydrogen ions relatively constant. And this is figure 2.17. Within organisms, most buffers consist of pairs of substances, one an acid and the other a base. The key buffer in human blood is an acid-base pair consisting of carbonic acid and bicarbonate. So carbonic acid is the acid, you all, and bicarbonate is the base. These two substances interact in a pair of reversible reactions. Let's see this now. First, carbon dioxide and water join to form carbonic acid, which in a second reaction dissociates to yield bicarbonate ion and hydrogen ion. If some acid or other substance adds hydrogen ions to the blood, the bicarbonate ion acts as a base and remove excess hydrogen ions by forming bicarbonate. If some acid or other substance adds hydrogen ions to the blood, bicarbonate acts as a base to remove excess hydrogen ions by forming H2CO3, which is carbonic acid. Similarly, if a basic substance removes hydrogen ions from the blood, carbonic acid dissociates, releasing more hydrogen ions into the blood. The forward and reverse reactions that interconvert carbonic acid and bicarbonate thus stabilize the blood pH. So I'll say that again. Carbonic acid is H2CO3. Bicarbonate is HCO3 negative. To say it one more time, if some acid or other substance adds hydrogen ions to the blood, the bicarbonate acts as a base to remove those excess hydrogen ions by forming carbonic acid. If a base substance removes hydrogen ions from the blood, carbonic acid dissociates, releasing more hydrogen ions into the blood. These reactions, forward and reverse reactions, they interconvert carbonic acid and bicarbonate, stabilizing blood's pH, and it remains between 7.35 and 7.45. That is when you're at homeostasis. You all should know that and remember that. The reaction of carbon dioxide and water to form carbonic acid is crucial because it permits carbon, essential to life, to enter the water from the air. The Earth's oceans are rich in carbon because of the reaction of carbon dioxide and water. In a condition called blood acidosis, human blood, which normally has a pH of about 7.35 to 7.45, I say again, when it drops to about 7.1. This condition is fatal if not treated immediately. The reverse condition is called blood alkalosis, which involves an increase in blood pH to a similar magnitude and is just as serious. This has been your instructor, Skylar Huff. Please take your time to go through the chapter. Use your chapter review, and even use the review questions and your visual summary. If you need me, reach out. I have office hours and an email, not to mention a telephone number. Thank you all for listening.